So let's solve recitation problem for chapter 15, the last chapter of Physics 101. So let's read this problem carefully. So here we have a physical pendulum. So we have a uniform rod of mass 2 kilogram and length 1 meter. It's suspended from a pivot point, which is at a distance 0.25 meters above the center of mass. Of course, it's uniform. The center of mass is right here in the middle. And you remember what is the moment of inertia, and it's passing through the center of mass. 1/12 of mass L squared. If this I call it M, of course. So the question is, what is the angular frequency in radian per second for small oscillation for this physical pendulum? Well, you know the formula. I demonstrated it in class. So omega is equal to square root of mgh divided by moment of inertia around the pivot point. Okay. So h here is equal to d, is the distance between the center of mass and the pivot point. So h is equal to d here. Moment of inertia, of course, will be the moment of inertia around the pivot point, not around the center of mass. So what is the moment of inertia around the pivot point? You apply parallel axis theorem. Okay, it's equal to the moment of inertia around the center of mass plus md square or mh square. H is, of course, the distance between the two axes, okay, which is d here. So that's it. Since I know everything, so I can get my omega in radian per second. You remember how to get this. Of course, we consider small oscillation. So we have our pivot point here, and we consider small oscillation. So the gravitational force is applied here, and you have a tension here. So, and then you apply net torque is equal to I alpha. And net torque here is only the torque of the gravitational force, because the torque of the tension is 0. It's passing through the axis of rotation. So it will be minus mg. This distance here is h, okay, sine theta. But you remember, for small angles, sine theta is equal to theta, and this should be equal to I alpha. So that means alpha, which is the angular acceleration, is theta point, meaning second derivative of the angle theta. Again, angle theta is this angle here, will be equal to minus mgh divided by moment of inertia multiplied by theta. And this is a signature of a simple harmonic oscillator. I have a second derivative is equal to minus a positive number multiplied by the function itself, which is the angular position here. So this is my omega. Okay, square, of course. Okay. So this is how we get omega is square root of mgh divided by I. Just to remind you, we already did this in class. And of course, you know that t is 2 pi divided by omega. So basically, this will give you 2 pi square root of I divided by mgh. Okay, and this is in your formula sheet. In your formula sheet, this is not there, but this is there. Okay? So know what you have and how to get the rest. The only difficulty in this type of problem is to get the moment of inertia. And of course, this h, to know that it's the distance between the two axes, parallel axes. Okay, when I do that, I get 4.1 radian per second. D is 0.25, of course, meters, which is L divided by 4. Let's go to the next problem. Same type of problem. Okay, so I have a solid circular disc is oscillating with a period t in a vertical plane about a pivot point P, as shown in this figure below. So this is a pivot point here. So if the disc is made 4 times heavier, but still have the same radius, what will be its period of oscillation? So first I have to find what is the period of oscillation of this disc. As we said, period of oscillation is 2 pi square root of I divided by mgh, because it's 2 pi divided by omega. Okay, so this is what I need. So now I need, so by the way, what is h here? it's a uniform solid disk. Okay, I did not say uniform, but you should guess that it's a uniform. So the axis of the center of mass is right here. So the difference, this h here is equal to what? Is equal to the radius. So the moment of inertia around P is a moment of inertia around the center of mass, and the center of mass is here, as we said, plus mass of the disk, h square, which is r square. So you remember here, if I put here the axis of rotation, moment of inertia, of course, around the center of mass is half mr square plus mr square. So the new moment of inertia around P is 3/2 of mr square, m being the mass of the disk. So the period will be what? 2 pi square root of I, which is 3/2 of mr square divided by mgr, because h is equal to r. Of course, it's independent of mass, and you simplify by your r, and you get what you need here. So basically it will be 2 pi square root of 3r divided by 2g. Okay. So this is a period. And as you see, the period is independent of the mass, because I have the mass on the moment of inertia, I have the mass on mgh, so it will simplify. So it's independent on the mass. It just depends on the radius. So if I keep the radius fixed and I multiply the mass by 4, well, I will still have the same period t. Good. Now let's go to this problem. Well, you get my point, okay? It will be the same thing. Of course, here they forgot about the 2 pi. Okay, so you have to add the 2 pi here. I divided by mgh. Here h is equal to d. And you apply, there is nothing difficult here, and you get the period in seconds. So in some problems, those who tape the solution, they are not physicists, they make mistakes, or they forget a factor. But you as a student, you should be able to get them. Okay, and know that, you know, I have to add a 2 pi here. So you look at your formula sheet, of course, you get t is 2 pi square root of I divided by mgh. What is I? Is the moment of inertia around the pivot point, and h is the distance from the center of mass and the pivot point, which is d. We solved this problem in class. I discussed this, so it does not depend on the period. You can demonstrate it and convince yourself. I already talked about this in class. It's a checkpoint in the book. Now let's go to this. Now we have a block which is attached to a spring that oscillates in a simple harmonic motion along the x-axis with an amplitude of x max. I did not give you x max. Of course, I did not give you the spring constant. Okay. Also, I did not give you the mass. Okay. The mass of the block. But I gave you the total kinetic energy. Now my question is the total mechanical energy. The total mechanical energy is 50 joules. And you know that mechanical energy is conserved, okay, in a simple harmonic motion, because I will neglect, in the case of a block attached to a spring, I neglect the friction. I will neglect air resistance, of course, if I have a pendulum. So mechanical energy is conserved. So the question is, what is the kinetic energy when x is equal to x max divided by 2? So 0, this is the amplitude, plus x max, and minus x max. So the amplitude is plus x max, of course. Okay, and then my object go back and forth. The question is, what is the kinetic energy when x is equal to half x max? I gave you the total mechanical energy. You know that mechanical energy is conserved, is basically kinetic energy plus spring potential energy here. So here it will be, it's conserved is half k x max square. I don't need to demonstrate this. You remember we demonstrated this in class, because you know that k is half mv square and us is half k x square. Okay, and well, you know that x is at any time is x max cosine omega t plus phi So V is the derivative. So it will be minus X max omega sine omega t plus phi. Okay. And then when I plug it, I know that, K is m omega square. We already talked about this important relationship. It's in your formula sheet. Write it down. This is also omega is square root of K divided by m. Okay. I'm just reminding, I already talked about this in class. So this we demonstrated in class, okay? Because we use the fact that, of course, sine square alpha plus cosine square alpha is equal to 1. And here, in here, I will have, of course, sine square, and here I have cosine square, and then I can show that the mechanical energy is conserved is 1/2 of K x max square. And this is equal to 50. Now the kinetic energy will be then 50, basically 1/2 of K x max square, which is 50, minus the spring potential energy. What is the spring potential energy? It will be 1/2 of K x square. Now x here is equal to x max divided by 2. So I have to take x max divided by 2 square. Replace x by x max divided by 2. So this will give me what? This will give me basically 1/2 K x max square. Here I will have 1/4, right? Okay. So I will have, so let me put 1/2 as a common factor. I'll have 1/2 of K as a common factor. I will have x max square minus 1/4 of x max square. So this will give me 1/2 K. Of course, I will have x max square. And here I will have what? 3/4. Okay. And this is 50. So I have 3/4 of 50. Okay. And this will give me 47.5 joule. And this is your kinetic energy when I'm here. Okay. Good. So this is what I used, and then you get it, and then you get your answer. This is 3/4, of course. Next. Okay, here I give you the mass of the block. I give you the spring constant K. So I'm giving you omega actually, because you know that K is m omega square, meaning omega is square root of K divided by m, just in case if I need it. So it oscillates in a horizontal frictionless surface. Of course, it's frictionless. That means I have what? Conservation of mechanical energy. Mechanical energy E is just 1/2 K x max square, okay? And it's conserved. Now I gave you x max. Of course, x max, you put it into meters, so 0.03 meters. So I can calculate what is my mechanical energy. It will be 1/2 of 20, 0.03 square, and you get your mechanical energy. So the question is, find the speed of the box when the displacement is 2.5 centimeters. Okay, good. So you know that the mechanical energy is conserved, right? Okay. So mechanical energy is conserved and is equal to kinetic energy plus spring potential energy or elastic potential energy. So kinetic energy is 1/2 of m v square. So this is the v that I want. And this is plus US is equal to 1/2 of K x square. So I gave you the x, okay? I'm asking you what is a V. And this is equal to 1/2 of K x max square. So first, what I can do, I will write K as m omega square. So I will have 1/2 of m v square plus 1/2 m omega square x square is equal to 1/2 m omega square x max square. And this I already demonstrated in class, but I already derived it. I'm showing you again and again, okay? So the 1/2 goes away, the m goes away, the mass goes away, okay? So I end up with what? V square plus omega square x square is equal to omega square x max square. Now, depending on the problem, here I gave you x max, of course, I gave you omega. Well, I gave you x, so I ask you v. So v will be what? Square root of x max square minus x square. Of course, you put everything in SI units. Okay. So this is what we did. Well, we did it kind of differently here. Okay. We just, calculated the mechanical energy here and then did it. But this will give you the same answer. Okay. Good. So this is it. So this is what he did. Also, you can use this directly. Of course, this is the same thing. Okay. And you get the answer. Okay, so an object executes a simple harmonic motion with an amplitude of 1.2 centimeters. X max is equal to 1.2 centimeters. So basically you put it in meters. Okay, and I give you the time, the period, 0.1 seconds. What is the total distance traveled by the object in 1.9 seconds? Well, just think about what we talked about in class. Okay, this is plus x max, this is minus x max. So let's assume that I start from here. Or let's assume that I start from x max. What is the period? The period is the time I take to do this, to go back to plus x max after passing by 0 minus x max coming back to 0. So in a period t, I'm covering a distance of 4 times x max, because I'm going x max, x max, x max, x max. In a period, I'm covering a distance of, in a period t, basically in 0.1 seconds, I'm covering a distance of 4 times x max. The question is, in a time of 1.9 seconds, how much distance I'm covering? Of course, it will be equal to what? Okay, so it will be equal to 4x max multiplied by 1.9 divided by 0.1. Okay, so it will give you 4. 1.2, of course, I put it in meters. Okay, multiplied by 1.9 divided by 0.1, and I will get the distance in meters. Okay, so I will get, of course, 0.912 meters, which is 91.2 centimeters. Okay, let's go to this problem. Well, we already demonstrated this. A simple harmonic oscillator has this amplitude, so I give you x max. It has this maximum speed, so here I'm giving you v max, okay, which is the amplitude of the velocity. You know that the amplitude of the velocity is omega x max, because when I have x, which is x max cosine omega t plus phi, if I derive, of course, I will have minus x max omega sine omega t plus phi. Okay, and the amplitude of the velocity is this, because this sign is between -1 and +1. So the absolute value, maximum v max, and this you should know it by heart, is omega x max. Okay, I already talked about it in class many times. I think it's not in your formula sheet, but you know it. Of course, acceleration, magnitude of the acceleration, or let's say amplitude of the acceleration, will be what? Omega square x max, and this you should know it as well. Okay, so here in a sense, I gave you x max and v max, so I gave you omega. So of course, omega will be equal to 8 radian per second. Okay, good. It will be just basically v max divided by x max. So now the question is, what is the speed when the displacement of the oscillator is 1.75 centimeters? We already discussed this, okay? So you can say that mechanical energy is conserved. Okay? Okay? And then you say that it will be equal to US plus kinetic energy. And we already demonstrated this. We said that you will have basically V square plus omega square x max x square is equal to omega square x max square. We already demonstrated this. So this gives you V is omega square root of x max square minus x square. Okay, here you see the mistake. This is a typo. They forgot the x square, but you know that it should be an x square, right? Good. You apply it and you get your answer. Okay, the displacement of a particle moving in a simple harmonic motion is given by this equation. Okay, so x is equal to 2 cosine of 60. So you know x max, where x is in meter and t in seconds. So I gave you x max is 2. Okay, omega is 6 radian per second. Of course, if I know omega, I know t. 2 pi divided by omega. But I also know f. F is equal to what? Omega divided by 2 pi. So what is the maximum acceleration of the particle? Maximum acceleration, well, I'm talking about the magnitude and where does it occur? Okay. So what do you need to know is basically acceleration max is omega square x max. So it will be 36 multiplied by x max, which is 2. So 72 meters per second square. So this will be the maximum acceleration. When does it occur? Of course, you know that if I have this is my 0, this is my plus x max, this is minus x max. The acceleration is maximum when my displacement is maximum. So it will be either here or here. In magnitude, they will have the same acceleration. But when I'm at plus x max, the acceleration is negative because of the restoring force. Remember, Fs is equal to minus kx, and Fs is ma. Okay, so when I'm at plus x max, the acceleration is at its maximum in magnitude, but negative. When I'm at minus x max, the acceleration is at going in the positive direction. So this is what I mean. If I just talk about maximum acceleration, it happens at plus x max and minus x max. Okay, but here I want also, you know, I am giving you the direction. I want you to tell me what is the direction of the acceleration. Well, the direction of acceleration when I am, because you know that the acceleration is doing like this, right? Okay, so x max can be either here in magnitude or here. Okay, but I'm talking, I want this when the acceleration is this. The acceleration is this at maximum negative displacement because the acceleration is positive. Here, acceleration is this, so this is 0 because this is the time. Okay, when I'm at plus x max, the acceleration is negative. So in magnitude, it's a maximum, but it's negative, it's below 0. So this is the only correct answer. This is not correct. If I follow the logic of the problem. Okay? So in physics, you always have this degree of interpretation. Okay? That makes a difference between students who just care about the final answer and students who want to understand what's going on. You have to put yourself in the mindset of the guy who is asking the problem. And real life is like that. When you go to Aramco, you work at Apple, you work at Sabic, you work at, I don't know, Facebook or Microsoft, the real problems comes, and then you use your analytical, critical thinking, you know, to see what are the relevant variables, what do they mean, etc., etc. Okay, so this problem is, you know, straightforward. You just look at, you know, at t equals 0, what is the x, what is the acceleration, okay? And then you get your phi, 105. Okay? So this is 4, that means this is 3, this is 2, this is 1. So you know that this is a form. Of course, that means acceleration will give you minus this. Okay? Because you derive 2 times. Okay? So this is A max. And A max here, we call it AS. And then you say at t equals 0, what do I have? Well, you have that this is equal to 1. So the only unknown is phi, and you get phi by cos inverse. Okay, this is a very important problem I want you to solve. Okay. So the question is what? What's the value of x? So here I put my pivot point here. Okay. I did not put it at the edge. I put it right here. The center of mass, of course, this is the physical pendulum. The center of mass is right in the middle because the pendulum is what? Uniform. So you have L over 2 here and L over 2 here. And I put the x here, the pivot point here. The distance between the, let's say, axis of rotation and the center of mass is x. So basically x here is equal to h, is equal to d, from the previous notation. So the question is, what value of x, okay, will give you the least period? So you know that period will be equal to what? 2 pi square root of I divided by mgh, which is mgx. Now what is this I? Of course, it's a rod. So you will have 1/12 of m L square, L being the length of the rod, and the length of the rod is given, plus parallel axis form m x square. Okay, so now I have a formula. So t is depending on x. It will be 2 pi square root of, so the m will go away. Here I will have 1/12 of L square plus x square divided by gx. Numerator I have x, denominator I have x. So the least period, I will have derivative of t with respect to x should be 0. When I am telling you the least or the highest, maximum or minimum of a function which is, a variable of another, function which depends on a variable, I should look at the derivative. Okay. When the derivative is 0, I have an extremum, maximum or minimum. So this is what we did here. Okay. So basically this is t, and we already discussed this. Okay. You can simplify by your m. Okay. And you have a square root. Now, if I want to get rid of the square root, let me take the square. Of course, I take square, I have this, and this is my function. Now, when does this function, when the derivative of this function is 0, so I do it, and I get it, so I get it, and then I get it here. Okay, I take square because it's easier to derive, but I can directly derive this. Okay, take the derivative of this gentleman with respect to x, and see which x it will be 0. Now, when I have that x, that's my answer. Now, once I get the x, I can tell you what's the period, what's the least period. Of course, I come back, I find this x here, and I plug it into my formula, and I get my period, and that will be the least period. This is also a very important problem. I gave you the solution. Okay, there is another way to solve it. I let you do it. Please solve all the rest of the problems. They are relevant and important. And inshallah, if you solve all this, you are ready for the final exam. I want you to solve this problem, this problem, this problem, everything. Okay. You will see that the idea is repeating itself, but it will be just a good practice for you. You solve this, you are good for the final exam. Okay. So I wish you the best, and I say assalamu alaikum. See you. Assalamu alaikum. So Bismillah ar-Rahman ar-Rahim wa salatu wa salam ala Rasulillah. So today we will solve review problems for the last 3 chapters. Okay. Chapter 15, chapter 14, and chapter 13. By the way, the mock exam, I will give you a couple of mock exams at the end of this week, and it will be available on Blackboard. And all the recitation problems related to these chapters are already recorded, and they are on Blackboard. Okay. So watch them, solve them, and make sure that you are comfortable with these problems. Okay. If you can solve the recitation problem, the exam will be a piece of cake for you, inshallah. Okay, let's solve the first problem. It's related to chapter 15. So let's read it. We have a 3 kilogram object. It is in a simple harmonic motion, okay, in 1 dimension. It moves according to this equation here. So here I gave you xm, of course, x max is equal to 5 cosine omega is pi over 3 radian per second, and phi is equal to minus pi divided by 4. Okay. Okay. So I know what is my amplitude, I know what is my angular frequency, and I know what is my phase, constant phase. Where t is in second, of course, x is in meter, because x max is in meter. The question is, how much time is needed for the object to move from its equilibrium position? Remember, equilibrium position means relaxed position, x equals 0. So how much time do I need to move from x equals 0 to a position where the potential energy is half of the total energy? Okay, so I need delta t when I start from x equals 0 to, this is my x initial, to x final is equal to what? I don't know x final, but I know the condition. At x final, the potential energy US is half the total energy, which is the total mechanical energy, half E. Okay, good. So this is a question here. First thing first, let me get the time when x equals 0. Of course, x equals 0 means 5 cosine pi over 3t minus pi over 4 is equal to 0. Okay? Meaning this cosine is equal to 0. Cosine is equal to 0 if the argument is pi divided by 2. Okay? Cosine 90 is 0. Okay? So that means I will have what? Pi divided by 3t minus pi divided by 4. It should be equal to pi divided by 2, which is 90 degrees. Okay. So this will give me the time. The time when I pass by x equals 0. So the time, let me call it t0. Okay. So I can simplify by pi, and I'll get t0 is half plus 1/4 multiplied by 3. So this will give you what? So here I will have 2, so I will have 9 divided by 4 seconds. So I will pass by position 0 when the time is 9 divided by 4 seconds. Okay. Now, what is the time when I've passed by XF? And XF is when I have US is half total mechanical energy. You know that the mechanical energy is equal to the spring potential energy plus the kinetic energy. Okay. And by the way, it's a constant. The mechanical energy is a constant. It's equal to half K X max square. Do you agree with me? And you remember that K is m omega square. Okay? Meaning omega is square root of K divided by m. Okay? Bottom line, the mechanical energy is constant, and it's equal to half K X max square. X max here being 5. Okay. Now, when I have US is the spring potential energy, is half K X square. X being here, X final. Okay. This is US. Okay. And US is half total mechanical energy. So basically, US is half of half K X max square. So I end up with half K X square is equal to half of half K X max square. I simplify by half, I simplify by k, and I end up with x will be what? Plus or minus x max divided by square root of 2. Okay. And this is a position at which I have spring potential energy is half mechanical energy. So the position xf that I'm looking for is this xf. Okay. It's basically x, which is equal to plus or minus x max divided by square root of 2. Let me take the positive value, okay? Let me just say plus x max divided by square root of 2. Now, this is xf, right? Which is x at tf. So it will give me what? It will give me x max cosine omega t plus phi. And by the way, I know what is xm, so I'll have xm cosine omega is pi divided by 3t minus phi is pi divided by 4. And this should be equal to x max divided by square root of 2. I simplify by x max, and I get what? I get cosine pi divided by 3t minus pi divided by 4 is equal to square root of 2 divided by 2. Which angle has a cosine square root of 2 divided by 2? So which angle has a cosine square root of 2 divided by 2? It's pi over 4, 45 degrees. Okay. So that means I can say that, let me write it here, pi divided by 3t, of course I'm talking about tf here, minus pi divided by 4 is equal to pi divided by 4, okay? So this cosine is equal to this cosine, that means this angle is equal to this angle. I simplify by pi, and I get tf is just 3/2 second. Okay. Now I know the time, t0, and I know tf. So delta t is the absolute value of tf minus t initial. Okay. And if I do it, I will find what? I will have basically 9/4 seconds minus 3/2 second. Okay. So if I do it properly, I will have what here? I will have 6 divided by 4. So basically I will have 3 divided by 4 seconds, which is 0.75 seconds. Okay. Does it make sense?
Yes, it is.
Okay. And this is a very good problem, and it's not an A+, but an A type problem. And we gave it a couple of years ago as an exam. Okay, so now let's look at this problem here. Simple harmonic motion again, chapter 15. So I have the motion of a particle in a mass spring system performing a simple harmonic motion is given by, I gave you here, x at any time is 25 centimeters, sine 10t. In general, I do this to confuse student, okay? In reality, in general, we write xm cosine omega t plus phi, right? But a cosine, I can write it as a sine. A sine, I can write it as a cosine. I just need to add pi over 2, actually. So don't be confused. If you have the choice, always use this form. X at any time is x max cosine omega t plus phi. Now, if the problem comes with a sign, you take it as it is. And no problem, you can solve the same thing, okay? Okay, good. So this is my x max. X max in meters is 0.25 meters, And omega is, of course, 10 radian per second, just by identifying this is omega. Okay. Now the question is, starting from a time t equals 0, by the way, at t equals 0, what is x0? Zero, because sine 0 is 0. So I'll have 25 sine 0, 0. Starting from t equals 0, find the time when the kinetic energy, so find the time t such that kinetic energy is twice the potential energy. Okay. So at which time and at which position in my spring mass system will I have kinetic energy is 2 times potential energy? Let me just draw it again, okay? This is my spring. It has a constant K. This is my block. It has a mass M. Of course, this is my equilibrium position. This is plus X max, and this is minus X max. And basically, it's going back and forth, okay? Oscillatory motion, okay? Between minus X max and plus X max. Okay? And in this process, if there is no friction, I am having a constant mechanical energy. And the spring potential energy is transformed into kinetic energy, and kinetic energy is transformed into spring potential energy, and vice versa, of course. Now, so the key is here. Like before, you remember before, I said potential energy, half of total energy. Okay? Here, I said kinetic energy, 2 times spring potential energy. You start by the mechanical energy. Mechanical energy is constant, and it's equal to kinetic energy plus spring potential energy, and its constant is equal to half k x max square. At x max, kinetic energy is 0, and my mechanical energy is purely a spring potential energy. Same at minus x max. I stop. So kinetic energy is 0. So, and then I showed you yesterday as a graph. Okay? The sum is constant, but kinetic or spring potential energy can be 0 or maximum, depending on where I am. At 0 here, the spring potential energy is 0, but the kinetic energy is max, and it's equal to the potential, to the mechanical energy. So this is what I have, and I know this for a fact. Now, second thing I know that K is 2 times US. So here, I'll say that E, which is the mechanical energy, which is half K x max square, is equal to, instead of writing K, I'll say 2 times US, because that's what I want. Yeah, I said that this is a condition, plus US. Okay, so this will give me 3 US. But you remember, US is a spring potential energy, is half K, the elongation at that point square. So I will end up with half K x max square is 3 times half K x square. Okay, so the half K goes away, half K goes away, and then I find that X is just plus or minus xm divided by square root of 3. So at the position when I have K, kinetic energy is twice potential energy, the displacement is x max divided by 3. Let me take the positive value. Okay. Good. And then I will do the same. I will say that X at this given time here is equal to x max divided by square root of 3. Now, if I use my equation here, I will say that X at that time is equal to x max sine 10t, x max being 25, right? And now my only unknown is a t. Now x max will simplify. So I'll have 1 over square root of 3 is equal to sine 10t. That means 10t is sine inverse of 1 square root of 3. Take your calculator. What is sine inverse of What is arc sine of 1 divided by square root of 3?
This 35.26.
Thank you very much, Hawam. MashaAllah. So 35.26. 26. Okay. 26. Okay. So this is in degree, but now you have to put it in what? Radian. So how many radian do you have? Because you remember, this is in radian.
It will be 89 divided by 450 pi.
Okay, so you know that pi radian, which is 3.14 radian, is 180 degree. That means 35.3 is equal to how many radian? Okay, so it will be basically what? 35 multiplied by pi divided by 180 degree. 35 degree multiplied by pi divided by 180 degree. So how much do you get in radian? The others, I believe I get 0.6 radian.
Yes, 0.62. Yeah.
Okay, 0.6. That means T is 0.6 divided by 10, and this gives you 0.06 second. And this is the answer. Okay? And this type of problem will come again and again and again. And by the way, I already solved the recitation problem on Blackboard. So watch the recitation videos. Okay? Thank you very much. Okay, any question? Hawam, you are the only one talking to me right now. So
no, it's clear, Doctor.
Excellent, mashallah. Okay, so now next problem is very simple. The period of a mass spring system, again a mass spring, performing a simple harmonic motion is T. When the mass is doubled, what is the new period? Well, you know that if I have a spring K and mass M system, and then I elongate it by X max, and I release it, it will be going from plus X max to minus X max, right? This is minus X max, and this is 0, okay? What is the period of oscillation? Who can tell me what is the period? It's in your formula sheet. And we talked about it.
2 pi over omega.
2 pi over omega, exactly. And omega is equal to what?
Root K over M.
Exactly, root K over M. So that means T, and this is in your formula sheet, is 2 pi square root of M divided by K. Okay, this is in your formula sheet. This is a period of a spring mass system. Now, if I double the mass, T prime, you will have the same thing. Now I will double the mass. Now the mass will be 2 times M and same K. So that means I will multiply by square root of 2 the old period. Okay, this 2 here was not appearing here. Okay, so if I double the mass, basically, let me call it here M prime. With M prime is 2M. Okay, so that means 2 prime, T prime is just square root of 2T. Okay, and I can play with that. I can double the mass and triple or quadruple the spring constant. And I will ask you what is the new period. You just play with the formula. Good. Okay, so we will finish by these two. Okay, I have to go faster. Now let's look at this problem here. I have an oscillator. Of course, it's a simple harmonic oscillator. Consists of a block attached to a spring. Again, mass spring, okay? This is my K, and I give you K 400. And I didn't give you the mass, but I will ask you the mass later. Of course, I elongated, and now it's going to from minus XM 2 plus xm, and oscillating back and forth, right? Okay. Now, at some time t, at a given time, the position measured from the system equilibrium location, basically x at a given time, x, the position, the velocity and acceleration are. So x is 0.1 meters. So let's say x is here, plus 0.1. Okay. X at this time is 0.1. And v at this time is minus 13.6, meaning I'm going in the negative direction. So it looks like I am leaving this plus x max here, and I'm going toward 0. Okay, so the velocity is given. V is minus 13.6 meters per second. And then I gave you acceleration. Acceleration is equal to minus 123 meters per second square. Now the question is this. First, calculate the frequency of oscillation. Second, calculate the mass of the block. And third, calculate the amplitude of the motion, xm. Okay. First, the frequency of oscillation, omega. How can I get the frequency of oscillation?
This is 1 over the period.
Say it again.
1 over the period. 1 over t. T capital.
F is 1 over t. But what is t?
2 pi over omega.
2 pi over omega. So F is equal to basically omega divided by 2 pi, right?
Yes.
Okay. But what is omega?
It will be km.
Okay. So omega is square root of k divided by m. But I know k, but what is m? That's the second question. Good. I like your way of thinking. Okay. This is how you do. You look at what you have and from your formulas and what you understood, how to go from one step to another. Okay. Now you see that I need to get omega. Once I get omega, I can get the frequency. Easy. Okay. But you said omega is square root of k divided by m. I know k, but I don't know m. Yet. I can know it, of course. That's the second question. Okay, now how can I do? Look at the data. The data I gave you is just x, v, and a. And I
use the energy theorem.
The energy theorem. So mechanical energy, which is constant, half k x max square. By the way, I know k, but I don't know x max, by the way. X max is the last question. Okay. And you said that this is equal to spring potential energy plus kinetic energy. Basically, half k x square plus half m v square. Okay. But I don't know k. I don't know m. Sorry, I don't know x max and I don't know m. But you get my point, okay? Good. I'm very happy that you said this, Hawam. Now, in one equation, I can get what is the frequency of oscillation. So it's a simple harmonic motion. If you remember, a simple harmonic oscillator, as I told you, xm, x at any time is xm cosine omega t plus phi. I can get what is the velocity. V is just the derivative, dx over dt. So this will give me what? Minus xm. Of course, the omega is coming out. Let me put it here. Minus omega xm sine omega t plus phi. And then from this, I can get the acceleration. Acceleration is the derivative of velocity with respect to time. So I will have minus omega square xm cosine, because I derive sine, I will have cosine omega t plus phi. And then I told you that, of course, this is x. So I will have acceleration at any time is equal to minus omega square multiplied by the position at that time. And this is a signature of a simple harmonic oscillator. Whenever I have a second derivative, which is minus a positive number multiplied by the function itself here. So acceleration is a second derivative of position with respect to time, or x dot dot. So this is a signature of a simple harmonic oscillator. The acceleration is proportional to the position, but opposite in direction because it's a restoring force. So now here, I know that at this time, the acceleration is 123 meter per second square. So it will be equal to minus omega square multiplied by the position at the time, which is 0.1. So I know what is omega. Omega will be just square root of 123 divided by 0.1, and I'll get it in radian per second. Okay. Now, once I get omega, I can get what is F in hertz. It's just omega divided by 2 pi. Frequency, as we said, is number of oscillation per second. Now, once I get omega, I plug it here. I know omega, I know K, 400. I can know what is the mass easily. So that's the second question. Okay. But for the first question, I have to use this. I have to use the data, X, V, and A. And I know each of them, so I have to use this to get it. By the way, let me remind you that the amplitude of the velocity is just omega xm. Write this down. And the amplitude of the acceleration is omega square xm. Also, this, write it down. Okay. I don't need it here, but in some problems you will need it. Okay, now I get omega and I got m. Now, what is the amplitude of motion? The amplitude of motion, as our brother Hawam said, we can use this mechanical energy. I will have half K, I know K is 400, xm square. By the way, I can, this is the question, amplitude of motion, xm. This will be equal to half K, I know K, x, I know x, 0.1. Plus half m, I know m now, I know it from the second question. V square, and I know V. V is this. And then I can get my xm. Okay? So this is exactly what I did. And the solution is here. Omega, we get this, 35.7 radian per second. F is omega divided by 2 pi. This gives you 5.6 hertz. Now I getting omega. Now I can get what is the mass. Easily, we just take square. So mass will be K divided by omega square. K is m omega square. So mass is just K divided by omega square. And I do it here. And I get the mass of the block is 0.325 kilogram. And then I use conservation of mechanical energy. Okay. I know K, I know M, I know X, I know V, XM is what I want to know, and it's 40 centimeters. How do you find it?
Little bit difficult, but step by step I will get the answer.
Inshallah. Okay. This is an idea, yes. Step by step. So remember, A is just minus omega square X. Okay. Next question. Okay. Well, this is also kind of, yeah, but let's look at it. This is my acceleration time graph for a spring block system that oscillate into a simple harmonic oscillator. Find the amplitude of oscillation. Basically, I want to find the X max, right? X max is the amplitude of oscillation. How will I do? Here I have acceleration. Okay. As we said before, acceleration will be just second derivative of velocity with respect to time, or second derivative of position with respect to time, knowing that position is xm cosine omega t plus phi. So if I take the second derivative, the acceleration will give me what? Minus omega square xm cosine omega t plus phi. Okay. but I will come back to that. And then from here, I can say that, of course, the amplitude, which is the maximum value of my acceleration, is omega square xm. And by the way, this problem is giving me the amplitude directly. It's here. So the amplitude is 0.2 meters per second square. This is the amplitude, okay? So of course, I'm going from A max to minus A max, and I see that it's 0.2 meters per second square. Okay? Now the problem is, what is omega? Omega, as our brother Hawam said, omega is 2 pi divided by t. So now I have to find t. What is t? I look at the period. I started from here, go down and up again, and here the period is this time here. So the period t is 0.8 seconds. So I can get omega is 2 pi divided by 0.8 seconds, and I have it in radian per second, of course. Once I have it, I plug it here, omega square, I know this. So of course, my x max is A max, which is 0.2 divided by omega square, which is this number here square. And you do it properly and you will get your answer. Now let me do, yes.
Yes, this t is equal to 0.8. Not mean the period only the 0.4, not 0.8.
Good question. The period is 0.8. So 0.4 is half the period.
Okay.
So what is the period? The period, I started from X max and I returned to X max. What is the time it took me to do this full oscillation? Okay, let's, A max, sorry. Okay, so let's say I will start it from here. The period is the time I take to go to minus X max and come back to plus X max. Okay. So the period here is the time I take to start from A max, go down to minus A, and then come back to plus A max. The period is a full oscillation. If you stop here, you did not look at a period. You are looking at half of the day or half of the period. The period is basically, today it's 8 right now. Tomorrow at 8, that's a full period. So you don't go half of it and you stop. The period is a time for a full oscillation. In a full oscillation, I started from here, I come back to the same position. Is it clear?
Yes, it makes sense now.
Yes. So be careful. Period, half period, a quarter of a period. So this is half period, t divided by 2. And this is a quarter of a period, t divided by 4. Okay, now let's go to a physical pendulum. So what do we have? In a physical pendulum, here, let's solve this problem, okay? So we have a uniform solid disk performing a simple harmonic oscillatory motion in a vertical plane. Okay? So this is my disk, it's a uniform solid disk. This is a vertical, of course. I deflect it a little bit because this is true for small angles, and I release it. Of course, it will be oscillating around this vertical fixed at this pivot point here. Okay, it will be going back and forth. But this is a physical pendulum. Okay? And a physical pendulum is different from a simple pendulum. A physical pendulum is anything, any object with a complex distribution of matter. A simple pendulum, well, that's easy. Massless rod, and the whole mass is focused at the bob. You deflect it a small angle, it will be going up and down. Okay? This is a simple pendulum. Here we have a physical pendulum. Okay, so it's performing a simple harmonic motion. When the disk is pivoted about a frictionless pin through a point R divided by 2 from its center, the period of oscillation is T. So when the axis of rotation is here, okay, the pivot point is here at R divided by 2 from the center of mass, the period is T. Now the question is, what is the period if the disk is pivoted at the rim? What is the period if now the pivot point is at the rim here, at R, what is the new period compared to the old period? Will it be T? Will it be 2 times T? Will it be T divided by 2 or half square root of T, 2T, etc., etc.? So the first T is when the pivot point is here, right? Pivot point is here, O. So period of a physical pendulum is formula sheet 2 pi square root of moment of inertia of the physical pendulum with respect to the axis of rotation here, which is O, divided by mgh. And h is the distance,
over 2.
the center of mass, and the pivot point. As our brother said, r divided by 2. Okay. Good. So h is r divided by 2. It's like in the parallel axis theorem. Okay. The distance between the new axis of rotation and the center of mass. Perpendicular distance, of course. Now, what is the moment of inertia? IO. I will use parallel axis theorem. It's equal to I center of mass plus mh square. I center of mass, you look at your formula sheet. Solid disk, uniform solid disk. What is the moment of inertia?
Half mr square.
Half mr square. Excellent. Plus mh square. H is r divided by 2 square. Yeah. So I will have what? Basically half plus 1/4 of mr square, which is 3/4 of mr square. Now let me come now to my period again. T, I will have 2 pi square root of 3 divided by 4 mr square divided by mgh. Mgh, h, which is r divided by 2, by the way. So you see the m simplifies. And the r here simplifies with this r, and I end up with a period which is equal to 2 pi square root of what? 6 divided by 4. Okay. R divided by G. Okay. So let me write it down again. It will give me 2 pi. 6 divided by 4 is 3 divided by 2, right? R divided by G. And this is my period of oscillation. Now, what about now I shift the axis of rotation from here to the rim here. So I shift it from here to here. The new period, let me call it T prime. It will be 2 pi square root of the new moment of inertia. Let me call it I prime divided by mgh. Now here, what is the h here?
R.
Thank you very much. R. Okay. So, of course, I prime, I can use parallel axis theorem. I center of mass plus mh square. So it will be half mr square plus mr square, which is 3/2 of mr square. Okay. So T prime will be 2 pi square root of 3/2 mr square divided by mgh. H is equal to r. The m, of course, simplify. Physical pendulum, the period of this physical pendulum does not depend on the mass. Okay. And you will have what? Of course, T prime is equal to 2 pi square root of 3 divided by 2.
R by divided by G.
And you see what? What do you see? Exactly the same. The period is the same. Okay. Good. Now, if I ask you a question, I will ask you, what should be the length of a simple pendulum that will have the same period? You know that the period of a simple pendulum is 2 pi square root of L divided by G. And this 2 pi square root of L divided by G should be equal to this. So that means that L here should be equal to 3/2 of R. Okay. A simple pendulum that will have the same period will have a length which is equal to 3/2 of R. Okay, good. Now, about this problem. I have a block of mass M attached to a spring K. Is performing a simple harmonic motion on a horizontal frictionless table. When the displacement from equilibrium is 3 meters, so x at this time is 3 meters, the speed v at this time is 40 meters per second. What is x max? And here I gave you m, 2 kilogram, and I gave you k, 200 Newton per meter. So what should I use here?
Mechanical energy.
Exactly. Mechanical energy is constant. Is half k x max square. I know k, but I don't know x max square. Let me get it. It will be US, spring potential energy, plus kinetic energy. Basically half k x square, by the way, I know x is equal to 3, plus half m v square. And I know m, and I know v. So I can get it easily. Okay. I will just say that half k x m square is just half k x squared plus half m v squared. I know everything here. Okay. Now, if I just say that, you know that if I divide by m, let me divide here by m, I divide here by m, and I divide here by m. So k divided by m is omega squared, right? So I will have half omega square x max square. So I already solved the problem. I'm talking about something else here. Okay. This will give me half omega square x square plus half v square. And this is what I told you yesterday. If I simplify by half, you end up with, of course, basically omega square x max square is equal to v square plus omega square x square. And this is true all the time. Yeah. And you know what is omega. Omega is just square root of k divided by m. I know k, I know m. So if I know one of them, I can get the second one. If I get two of them, I can get the third one. Here I know v and I know x. I know omega, k divided by m. So I know what is xm. Okay, I took a lot of time on chapter 15, but alhamdulillah, let me go to this chapter. And again, for this chapter, I posted a 1-hour video solving, fluid mechanics, okay? Fluid statics and fluid dynamics, hydrostatic and dynamics. So let's look at it quickly. I have a pipe. Water is flowing through the pipe, which is shown here. Okay? So what do I have? Water speed through the lower pipe is 5 meters per second. You can see it here. So V1 is 5 meters per second. And the pressure here, the gauge pressure reads 75 kilopascal. Okay. Again, gauge pressure is the pressure of the liquid minus atmospheric pressure. Okay. And this is equal to 75 kilopascal. Okay. Good. And then at this turn here, okay, at this end of the pipe, which is 2 meters higher than the first section, and which has a diameter basically of 4 centimeters. Here the diameter is what? 6 centimeters. The question is, what is the pressure here? What is the gauge pressure here? So P2 minus P0. What is it? Okay, here is P1 minus P0 is 75 Pascal. Of course, I will be using Bernoulli equation and continuity equation. So I will look at the streamline. So along this streamline, I can apply Bernoulli equation. The Bernoulli equation will give me P1, meaning pressure here, plus half rho V1 square, which is the dynamic pressure, okay, half rho density V1 square, plus rho G Y1, and of course I will take Y1 to be 0, and y2, I will take it to be 2 meters. This is equal to P2 plus half rho. So here there is a rho. So you correct these type of things, okay? Sometimes in the solution, you have typos, but now we are at the end of the semester. Mashallah, you are mature and you are able, you can get married soon, inshallah. After you finish 101, you can get married because you gain in maturity. Okay, half rho V1, V2 square plus half plus rho GY2. Okay. Again, here the pressures are known. P1 minus P0 is known. Now the question is, what is P2 minus P0? If I retract P0, it's the same. Okay. Because I'm talking, technically I should say P2 minus P0 here. Okay. I should put a minus P0 and I should put a minus P0 here because this is what I gave you. I gave you P1 minus P0 and this is 75 kilopascal. So P2 will be P1 and I know P1, basically P1, I know it from P1 minus P0, which is 75 kilopascal. Okay. And then now I will have half rho V1 square minus V2 square plus half rho G2, rho G Y1 minus Y2. Okay. So I know that this is equal to minus 2. Y1 minus Y2 is minus 2. Now what is V1 minus V2? I will use continuity equation. I know that the volume flow rate is constant. A1 V1 is equal to A2 V2. That means V2 is A1 divided by A2 multiplied by V1. Now I can calculate it, okay? Because here it's a pipe. So it has a circular shape, kind of cylindrical shape here. Okay? What is the cross-sectional area? It will be pi r square. Okay? Okay. So I will have basically V1 multiplied by pi r1 square is equal to V2 multiplied by pi r2 square. So the pi, of course, will go away. So I will have V2 is equal to V1, which is 5 meters per second. Okay, and then I will have what? Basically R1 divided by R2 square. And R1 is equal to 6. R2 is equal to 4. Sorry, half of them. Okay, because I'm talking about the radius, but it doesn't matter. Okay, because it will be 6 divided by 2, 4 divided by 2. Okay, because here I gave you the diameters. Of course, the half will go away. And here you will just have this, and it will give you V2 is 11.25 meter per second. You know everything, and you plug it in your Bernoulli equation, and you will get P2. Okay. So this is the P2 that I get. And be careful here a little bit, okay? Because here I'm talking about gauge pressure. But here they were nice. Actually, they should have talked about absolute pressure because you don't need the gauge pressure. Gauge pressure is absolute pressure minus atmospheric pressure. Okay, I have 2 minutes or 1 minute. I wanted to solve this problem. I wanted to solve this problem. I wanted to solve this problem. And I wanted to go to chapter 13. On chapter 13, I posted 2 nice recitation recordings about the problems that I found most important. But I did not have time to solve this one. This is a very important problem. This is also a very important problem, okay? But I will solve it with the other sections and I will put the recording online. So thank you very much. It was a pleasure teaching you Physics 101. Inshallah, I pray for you. You keep me in your prayers, in your dua. And inshallah, I will see you next time. But before you leave, let's take a family picture, if you don't mind.